Hello students, welcome back. Let's resume our discussion. Previously we talked about the partition, and then using the concept of partition we defined the Riemann sum. Here's a visualization. A Riemann sum is basically a sum of the areas of these rectangles given by a subinterval width delta xi times the y-coordinate yi star, which is randomly selected y-coordinate in between the minimum and maximum. Due to the randomness, if I run the program again, I get different y-coordinate values, so different heights. So basically you're looking at the sum of areas of rectangle. There's a bit of a problem here. Take a look at this part especially. If this point down here is emptied out, then the minimum doesn't exist. The maximum exists here, it's continuous over there. But down here, if it is solid dot, then okay, but emptied out, then minimum does not exist. So this expression down here is invalid because the minimum doesn't exist. So we change it into a little bit different notation by introducing a new concept of the infimum and the supremum in place of minimum and maximum. And they work exactly the same as the minimum and the maximum, except that they always exist. So down here, minimum does not exist, so this entire thing may be invalid. No sweat. Change over to infimum, then it's this dotted value right here. So we have the perfect definition of the Riemann sum. Perfect, not just for this course, but in graduate level as well. So this is a Riemann sum. And then here is a bit more simplified version, which will work well for continuous functions. But then again, in this course, almost all the time we're going to study only continuous functions. This is calculus 2, not something super hard. So let's reduce even further. In case of continuous functions, this yi star can be rewritten as f of xi star, because I can always find yi star between the minimum and maximum, where yi star is f of xi star, where xi star is selected somewhere in this subinterval. The existence of minimum and maximum is called the minimum maximum theorem for a continuous function defined in a closed interval. And then for anything in between, the existence of this x-coordinate value is called intermediate value theorem for a continuous function in closed interval. But both are difficult, so let's not go too deeply into this. Let's just stick to the core. This yi star can be replaced by f of xi star, and that randomness of yi star can be passed on to the randomness of xi star anywhere in between x of i minus 1 to xi. Here's a visualization. So any yi star here in the first interval, third interval, or fourth interval, you can find out appropriate xi star down here as blue dots so that the function values are the y-coordinate. But that doesn't work for the red rectangle here because there's no crossing due to discontinuity. Let me run this again. And then this time I get very different the xi stars, still no corresponding. You see, look at the third case here, and there are two crossings, so I could have selected this one or that one, but I selected the right-hand side one here. It's okay, anything will do. In this case, we have crossings, so this would have worked for red rectangle again, but in general, it doesn't. In general, it doesn't. So for continuous function, we have this reduction. So far so good, but still too hard. Okay, still too difficult. So let's restrict ourselves even further down. Let's consider only the evenly spaced partition. So instead of taking partitions like this with variable width, we take the partition with same width, so that delta xi's are all the same, and that is b minus a over n, the width of the original large interval divided by n, the partition's number. So there's no randomness in the x-coordinate, so width of those rectangles are all the same, but there's some randomness here, so height will change. Let's visualize these. First, the arbitrary Riemann sum for continuous function. Yeah, okay, as you can see, we have a continuous function. And then I'm selecting xi star randomly between any xi minus 1 to xi, but even more, I'm selecting xi's at random too. Just randomly selected 21 points. Actually, randomly selected 19 points because x0 and x20 are fixed as the starting and ending points. In this case, -2 and +3 respectively. And then because of all these randomness, we have really wild rectangles here and terrible approximation. Especially look at these fat rectangles. Terrible approximation. And the Riemann sum here is very different from the definite integral value. That's because of the randomness. And then, of course, if I run it again, I get wildly different rectangles and then wildly different Riemann sum values. Terrible way to approximate. But why would anybody do it this way? Well, they don't. They do not use this kind of approximation because they are terrible. In theory, however, these are useful because in theory, we want to prove that everything will go to the definite integral. So we want as bad an approximation as possible. And even that is going down to the definite integral or going up to the definite integral, whatever you may call. So in terms of theory, the arbitrary Riemann sums are necessary. In terms of practical computation, these are useless. Much better way is this one, but still it's a bit of a tweener, you see. Evenly spaced. So if you look at the rectangles, width of those rectangles, they're the same. Heights of those rectangles change because of these randomness here. Xi stars are random. So you get much better approximation here, but still, this is not really practical in terms of in terms of computation either, because of the randomness, of course. We don't want those randomness if you really want to do some computation. In terms of theory, it's too good because a lot of bad cases are actually slipping between your fingers. And theoretically, you cannot prove anything. So you're going to get the worst possible case. And then even there, we have convergence. So everything is good. That's basically what you want to establish. And that's why we want that wild, terrible, just those wild, terrible cases like these. That's why we wanted those. But this one is a tweener. In terms of theory, it's not wild enough. In terms of actual computation, it's too wild. Okay, let's go to the next. This time there's no randomness. Even if I run this again, I get the same result again. Xi stars are not selected at random, but I select as the midpoint of the subinterval, xi minus 1 plus xi over 2. So look at this rectangle here. Xi minus 1 is here, xi is there, right in the middle. Xi minus 1 is here, xi is there, right in the middle. We take the midpoint, and the function value of the midpoint is the height of the rectangle. In order to see this better, I'm taking only 10 intervals. But despite just 10 intervals, I get very decent approximation. That's one way to use the midpoint. It's called the midpoint approximation. Now, another way to use the midpoint approximation is to do this. Instead of using the midpoint of x-coordinate, let's use the midpoint of y-coordinate. This yi star is arbitrary in theory, but instead of taking arbitrary and getting some wild approximation, let's do this. Yi minus 1 plus yi over 2. So the left-hand side point, right-hand side y-coordinate value, and then right in the middle. Left-hand side point, right-hand side point, right in the middle. Left-hand side y-coordinate, right-hand side y-coordinate value, right in the middle. This picture turned out to be a bit confusing because it gives you an illusion that I'm taking the midpoint of maximum and the minimum, but no, minimum and maximum are not involved. Let me change this number to something else. Okay, you see the maximum is not involved at all. Left-hand side endpoint, yi minus 1. Right-hand side endpoint, yi. And then I'm taking the average of the two. Again, the next rectangle here, yi minus 1. So left-hand side y-coordinate value, yi, right-hand side y-coordinate value, and this is the average of the two. See what I'm talking about here? So yi star loses the randomness and become yi minus 1 plus yi over 2. We can take the midpoint. We can take the midpoint either through x-coordinate or to y-coordinate. Either way, it works out. It'll turn out, however, this y-coordinate case is the same as trapezoid approximation because this expression here, with some algebraic manipulation, becomes like that. With minimal algebraic manipulation, multiply delta x over there, and this is trapezoid area formula of this each trapezoid. So instead of using rectangles, if you join those points and form those trapezoids, as you can see, those areas, and add up the areas of trapezoid, then it's the same as this Riemann sum. As a matter of fact, you can see these together in the same viewing window like this. Left-hand side is the previous Riemann sum. We have rectangles given by yi stars, which are, as a matter of fact, the average values, so left-hand side and right-hand side. And here, the trapezoid. Looking at first glance, this approximation looks like better approximation than this, because you see there are less white parts. But actually, these two quantities are the same. So midpoints are actually good. Either you take the x-coordinate or y-coordinate. Now, how about the left-hand side and right-hand side approximation? These are not as good. As you can see, numbers are less good compared with the midpoint approximations in terms of approximation. And then looking at the picture, a lot more white parts. Let's see, here, this is left-hand side approximation. As a yi star value, we take the function value of left-hand side. So yi minus 1. Here, as a yi star value, we take right-hand side function value, yi. And then look at the next rectangle here. Here I take left-hand side endpoint, yi minus 1. Here I'm taking yi, the right-hand side endpoint. So left-hand side and right-hand side approximations, again, no randomness. And then they are Riemann sums too. But in terms of approximation, they're not very good. But there are some cases that left-hand side and right-hand side endpoints are very, very useful. We're going to discuss those in separate videos. So we went through Riemann sums and various visualizations. Now let's do some application problems in the next video.